You ever stop and really think about the invisible magic that connects your phone to, well, everything? It just works, right? But behind that super smooth experience, there's a century of absolutely brilliant engineering. So today, we're going to pull back the curtain and demystify the tech that powers our entire connected world. So let's just dive right in with the big question. You hit send on a video, and like seconds later, your friend on the other side of the planet is watching it. How on earth is that even possible? Well, the answer doesn't start with phones or towers. It starts with some basic physics. Everything, and I mean literally everything, in wireless communication boils down to electromagnetic waves. Now, before we can get how they carry our TikToks and emails, we first have to understand what they even are. And believe it or not, our journey starts with something super simple: color.
So when you see the color cyan, what you're really seeing is your eyes in your brain interpreting waves of energy that are oscillating over 600 times trillion times a second. It's not about the color itself, really. It's about the properties of the wave that's creating it.
And the most important property here is wavelength. That's just the physical distance from the peak of one wave to the next. If you change that distance, you change everything about the wave. A wave that's 486 nanometers wide, your brain calls that cyan. But if you shrink it, it becomes purple. Stretch it out a bit, it becomes that.
Now, this is where it gets really cool. Depending on that wavelength, the properties change dramatically. If you squeeze that wave down to the size of an atom, you get X-rays that can pass right through your skin. But if you stretch it way, way out, so it's meters or even kilometers long, you get radio waves. And their special trick? They can travel huge distances and go right through obstacles like buildings. That right there is what makes them absolutely perfect for communication.
Okay, so we've got our delivery truck, the radio wave. But a plain empty wave isn't carrying any information. The next big problem to solve was, how do you make that wave talk? How do you actually encode your data onto it? The first methods were pretty straightforward, and you already know them from your car stereo: AM and FM radio. With amplitude modulation, AM, you just make the wave stronger or weaker. With frequency modulation, FM, you kind of scrunch the waves closer together or stretch them farther apart. You're basically drawing a copy of the sound wave with a radio wave. It works, but it's not super efficient for sending complex stuff like video.
The real game changer was the switch to digital. Instead of trying to mimic a sound wave, engineers realized it's way better to convert everything into the language of computers, binary code. Just a long, simple stream of ones and zeros. It's so much more efficient and way more reliable. And going digital opens up all these new tricks. One of the coolest is called phase modulation. So think about a wave cycle. We can just decide that if a wave starts by going up, that's a 1, and if it starts by going down, that's a 0. Just by doing that, we can send our binary code at an incredible speed. But here's where the engineers got really, really clever. They thought, why just mess with one property of the wave when we can mess with two at the exact same time? So they started combining different phases with different levels of amplitude or strength. And this is the result of that thinking. It's just amazing. Instead of just up or down for a 1 or a 0, they can now create 1,024 unique, distinct combinations of phase and strength. Each one of those combinations represents a whole chunk of binary data. That's how we can cram a mind-boggling amount of information into one single tiny radio signal. All right, so we've figured out how to send a ton of data on a single wave. Awesome. But how do you build a system that lets millions of people in one city do that all at the same time? That is a totally different problem, a problem of scale. The very first car phones were incredibly limited. They had one giant, powerful transmitter for an entire city, and that meant only about 32 people could make a call at the same time. 32! The massive breakthrough was the cellular concept. Instead of one big transmitter, why not use lots of little ones? And this is basically what that idea looks like. You split a region into this honeycomb of smaller areas, or cells, and each one gets its own low-power tower. This is the whole reason we call them cell phones. And the genius part is, you can reuse the same radio frequencies in different cells as long as they're not right next to each other. This just massively multiplied the number of people who could use the network. So you might be wondering, how do these towers actually connect to the internet? Well, it's surprisingly simple. Most of them are literally plugged into the ground with a physical fiber optic cable. But for those really remote spots, like a tower way up on a mountain, they use these highly focused microwave dishes to just beam the signal to the next closest tower that is connected. Okay, we've built the network.
But now we hit the biggest challenge of all. The airwaves, the radio spectrum, it's not infinite. There are only so many frequencies to go around. So how in the world do you get millions of phones to share this one incredibly crowded resource? And this chart just shows you how tight that squeeze really is. To stop signals from messing with each other, a cell can't use the same frequencies as the cells right next to it. Because of that rule, any one cell can only use about 1/7 of the total channels available. Back in the day, that left you with only about 56 channels per cell. For a whole city, no way. Not even close. So the first clever trick was something called TDMA, or Time Division Multiple Access. The idea is brilliant in its simplicity. Just take turns, but do it really, really fast. You take one radio channel and slice it into tiny little time slots. Your phone gets assigned one slot, it sends a quick burst of data, and then it waits for its turn to come back around. Just like that, one channel that used to serve one person can now serve 8. Pretty smart. Time slicing was a huge step. But, engineers, they're never satisfied. They started asking a crazier question. What if we didn't have to take turns at all? What if everybody could just transmit on the exact same channel at the exact same time and it would all just work? And the answer to that crazy question was CDMA, or Code Division Multiple Access. The best way to think about it is like being at a really loud party. There are dozens of conversations happening at once, but you can still focus on your friend's voice because you know what it sounds like. With CDMA, your phone's data gets mixed with a unique digital code. It's like a secret handshake. The tower knows your phone's specific code, so it can listen for that unique voice in all the noise and pull your data right out.
So let's just zoom out for a second. From figuring out how to make a wave carry ones and zeros, to splitting up cities into a honeycomb of cells, to giving every phone a secret code so they can all talk at once, the entire history of cell service is just this incredible story of one brilliant innovation after another.
There's this quote from the source material that just nails it perfectly. The whole challenge comes down to two things. First, packing as much data as you can into one single transmission. And second, packing as many of those transmissions as you can into the shared airwaves. That's the whole game. Every single innovation we've talked about is a solution to one of those two problems. So the next time you look at your phone and you see that little icon switch from 4G to 5G, you'll know exactly what's happening. It's not just about getting faster. It's the result of smarter ways of encoding data, like those 1024 combinations, and more efficient ways of sharing the airwaves. Each generation, is really just the story of engineers finding a more ingenious way to solve that fundamental packing problem. And that, of course, brings us to what's next. Our hunger for data, for streaming, for gaming, for things we haven't even thought of yet, it's only going up. The engineering challenge is exactly the same as it's always been. So the final question is, what's the next brilliant, mind-bending breakthrough that's going to let us pack even more into the invisible waves all around us?